What if I told you that deep beneath your feet, the earth is running a natural spa? It's true. Rainwater, on an incredible journey miles into the crust, is being boiled by the planet's internal furnace before returning to the surface as a therapeutic, mineral-rich hot tub. How on earth does this happen? The answer is a story of immense pressure, intense heat, and a hidden world of geological wonders. It all begins with something incredibly simple, a single drop of rain. But this is no ordinary water. This is water destined for an epic adventure, a transformation that will turn it into one of nature's most spectacular and soothing creations. So, how does a simple raindrop become a boiling, bubbling hot spring? The forces at play are more incredible than you can imagine. Our story starts in the clouds. A drop of water falls as rain or snow. For most raindrops, the journey is short. They'll just flow into rivers, lakes, and oceans. But for some, the destination is far more profound. It lands on the ground and begins to seep downwards, pulled by gravity through porous soil and rock. This is the first critical step: infiltration. The Earth's crust isn't a solid, impenetrable shell. It's a complex network of permeable rocks, fractures, and faults, tiny highways leading deep underground. Our water droplet finds one of these paths and begins a descent that could take it thousands of feet below the surface. This isn't a quick trip. In places like Hot Springs National Park in Arkansas, this downward journey can take thousands of years. Imagine a sponge the size of a mountain range. The water slowly works its way through these intricate passages, venturing deeper and deeper. It leaves the world of light and life behind, entering a realm of crushing pressure and rising temperature. This is where the real transformation begins. As our water travels deeper, the world around it changes dramatically. For every kilometer it descends, the temperature of the surrounding rock increases by about 25 to 30 degrees Celsius. This steady increase is known as the geothermal gradient. It's heat generated by the slow decay of radioactive elements within the Earth's crust and leftover heat from the planet's formation. In many parts of the world, this is the sole engine heating our natural hot tubs, a slow, patient warming process over millennia. But in other, more dramatic locations, there's an express lane to boiling. In geologically active zones like Iceland or Yellowstone National Park, massive chambers of magma molten rock from the Earth's mantle sit much closer to the surface. These magma bodies can reach temperatures over 700 degrees Celsius or 1,300 degrees Fahrenheit. As groundwater seeps near these blistering heat sources, it's heated rapidly and intensely. Think of it as the difference between a slow cooker and a blast furnace. Whether heated slowly by the geothermal gradient or rapidly by a magma chamber, the result is the same. The water becomes superheated, often to temperatures far beyond its normal boiling point. The immense pressure from the miles of rock and water above prevents it from turning into steam, keeping it in a volatile, superheated liquid state. Our simple raindrop is now a powerful force of nature. This superheated high-pressure water is more than just hot. It's a powerful solvent. As it circulates through the deep, hot rocks, it starts dissolving them from the inside out. Like hot tea dissolving sugar, the water pulls minerals directly from the rock it passes through. This is where each hot spring gets its unique personality. The water becomes a complex cocktail of dissolved solids. Depending on the local geology, it might pick up high concentrations of silica from granite or calcium carbonate from limestone. It can become rich in magnesium, potassium, lithium, sodium, and even trace amounts of elements like iron and sulfur. This distinct mineral content is what gives different hot springs their reputed therapeutic properties, a practice known as balneology that dates back centuries. For example, the waters at Glenwood Hot Springs in Colorado are famous for containing a potent mix of dissolved minerals, including boron, magnesium, calcium, and potassium. The waters of Bath, England, percolated through deep limestone, becoming rich in calcium and sulfate. These mineral signatures are a direct record of the water's long subterranean journey, a chemical passport stamped by every rock formation it has encountered. Now, our water is superheated and saturated with minerals. But how does it get back to the surface? Simple physics. As the water was heated, it expanded and became less dense, more buoyant than the cooler, denser water sinking from above. This creates a powerful convection current, a slow but unstoppable drive to rise. The same network of faults and fractures that allowed the water to descend now becomes its escape route. These geological plumbing systems act as conduits, channeling the hot, pressurized water upwards. In some places, these pathways are the result of ancient mountain-building events that folded and cracked the rock layers, creating perfect channels for water to circulate. Hot Springs, Arkansas, is a prime example, where 400 million-year-old folded rocks provide the route for water that's been underground for 4,000 years to finally reach the surface. This upward journey is a race against time. The water must travel quickly enough through these fissures to retain its heat. Propelled by the immense pressure from below, it forces its way through the crust to emerge, steaming and bubbling, into the open air. The final leg of its journey is often the most dramatic. When this geothermally heated water finally emerges, it can create a stunning variety of features. The form it takes depends entirely on the underground plumbing and the amount of heat and water in the system. The most serene of these are the hot springs themselves, those tranquil, natural hot tubs where water pools gently. These are places where the plumbing system allows water to rise without major obstructions. But if the plumbing is constricted, things get much more exciting. This leads to the formation of geysers. A geyser requires a specific underground structure, a reservoir for water, and a series of tight constrictions in its plumbing. As water fills the system, it's superheated by the geothermal source. Steam bubbles form at the bottom, but their path is blocked. Pressure builds and builds, until the trapped steam violently forces the column of water above it out of the vent. This sudden pressure drop causes much of the remaining superheated water to flash into steam, powering a spectacular eruption of water and vapor, like the famous Old Faithful in Yellowstone. If there's plenty of heat but not much water, you get a fumarole, or steam vent. The water boils away before it reaches the surface, releasing clouds of steam and volcanic gases. And in areas with acidic water, another feature appears, the mud pot. Here, the hot, acidic water dissolves the surrounding rock into a bubbling, viscous clay, creating a primordial-looking cauldron of boiling mud. The spectacle doesn't end when the water reaches the surface. As this mineral-laden water cools and evaporates, it leaves its dissolved cargo behind, building incredible structures over thousands of years. In areas where the water is rich in calcium carbonate, it forms a rock called travertine. As the hot water emerges, the drop in pressure releases carbon dioxide gas, much like opening a can of soda, causing the calcium carbonate to precipitate out of the solution. This process creates the magnificent, wedding cake-like travertine terraces seen at places like Mammoth Hot Springs in Yellowstone or Pamukkale in Turkey. These cascading pools are constantly changing, as new layers of limestone are deposited day by day. Where the hot water has dissolved silica from volcanic rock, it forms a different kind of deposit known as siliceous sinter or geyserite. This hard, glassy substance coats the plumbing of geysers, making them strong enough to withstand the pressure of their eruptions. The otherworldly cones and delicate formations around many of Yellowstone's geysers are all built from this sinter. Often, the vibrant colors in these deposits, the oranges, yellows, and greens, aren't from the minerals themselves, but from vast communities of thermophiles, heat-loving microbes that thrive in the hot, mineral-rich water. These geothermal wonders are more than just beautiful spectacles. They're invaluable scientific laboratories. Geologists study them to understand the hidden processes of our planet, from volcanic activity to the movement of tectonic plates. The chemistry of a hot spring provides a direct sample of the deep crust, offering clues about the composition of rocks miles below. And here's where it gets truly mind-bending. Some scientists believe environments like these may hold the key to understanding the origin of life on Earth. The chemical-rich, energy-filled waters of ancient hot springs could have provided the perfect cradle for the first complex organic molecules to form. Some of the oldest evidence of life on land, dating back nearly 3.5 billion years, was found preserved in ancient hot spring deposits in Australia. By studying modern hot springs, we get a glimpse of what our planet might have looked like in its infancy, and we learn what to look for when searching for life on other worlds. The cryogeysers on Saturn's moon Enceladus and the signs of past hydrothermal activity on Mars make these earthly hot springs a vital roadmap for astrobiology. So, the next time you see a steaming hot spring, remember the incredible journey that made it possible. It's a story that starts with a single drop of rain on an epic, 1,000-year odyssey deep into the Earth's crust. It's a story of being cooked by the planet's internal engine, infused with a cocktail of ancient minerals, and finally returning to the surface through a complex and violent plumbing system. From serene pools to explosive geysers and primordial mud pots, these features are a dramatic reminder that our planet is not a static ball of rock. It's a living, breathing, dynamic system with hidden wonders being forged deep beneath our feet. The Earth isn't just running a spa, it's putting on a spectacular show of geological power. If you found this journey as amazing as we did, don't forget to like, share, and subscribe for more science made simple. Let us know in the comments which of these geothermal wonders you'd most like to see for yourself. Thanks for watching.